compare the IE1, then we can say that okay, IE1 for chromium will be less as compared to manganese. Why? Second ionization energy of copper is very high, we know, because the Ziegler-Natta catalyst, that is the combination of titanium chloride and... Hello dear students, welcome to Alan Overseas and welcome back to the very important series, that is 45 important topics in 45 days. Okay. So as you know, this series is divided into 3 parts, that is 15 topics from physics, 15 from chemistry as well as 15 from mathematics, and this is how we are going to cover our 45 important topics, right? So you know, I will be covering the chemistry part. Now let's see what we have here, the next topic of the chemistry, okay? So, the next topic is important properties of D and F block elements, that is taken from the chapter D and F block elements, okay? Fine. So, right, let's start this topic. Okay, first of all, we have this very important topic from this D block elements, that is ionization enthalpies, right? So, let's discuss about them. In general, ionization energy increases with irregular trends from left to right in a series, okay. Generally, when we talk about the ionization energy, what is ionization energy? Ionization energy is the minimum energy required to remove an outermost shell electron from the gaseous isolated neutral atom, right? And generally, when we compare this ionization energy in the periodic table in a particular group or in a period, then we say that in a period left to right it increases and in a group top to bottom it decreases, okay. So we see the regular trends when we talk about S block elements and P block elements generally, but for the D block elements we don't have this regular trend, okay. When we talk about a particular series like 3D series, 4D series or 5D series, these trends are very irregular, right? So when one electron is basically removed from NS orbital, relative ionization energy of 3D and 4S changes and the other NS electron shifts to the N-1 d orbital. This is very important point. Okay, when we talk about the D block elements, they have this irregular trend of ionization energy. So we cannot find a regular trend, but still we can discuss some important points regarding the ionization energies. And this is the very first important point regarding that. Okay, so when you are removing one electron, okay, in D block elements, what is the general electronic configuration? General outermost shell electronic configuration is 3D 1 to 10, and in 4S you have either 0 or max to max you can have 2 electrons, okay. This is your general outermost shell electronic configuration. So when you remove, suppose in 4S you have 2 electrons, right? So when you have removed 1 electron from the 4S, now what will happen? The remaining 1 electron in the 4S will shift into 3D orbital, okay, 3D orbital, and that will be the configuration of that ion. For example, if we talk about how many unpaired electrons are there in Fe+, okay, iron plus oxidation state. So first of all, if we talk about the electronic configuration of iron, that is argon, okay, and in 3D you have 6 electron, in 4S we have 2 electrons. This is the electronic configuration of iron. So if I talk about Fe+, Fe plus means you have removed 1 electron from the 4S, right? So what will be left? Argon 3D 6, 4S1. Now what will happen? This one electron from the 4S will shift into this 3D orbital, and ultimately what you will get? You will get argon 3D 7, and in 4S you have 0 electrons now, okay. So now the electronic configuration becomes 3D 7. So now when the next electron will be removed, that will be removed from this 3D 7 electronic configuration, okay. This is very important point about these D block elements, okay, right. So this will be your electronic configuration for Fe+. Okay, and yes, this will be taking place when there are ligands around this metal, okay, when there are some other molecules around this metal, then this thing will be taking place, right? Now, let's see the next important point, that is IE2. That is second ionization energy of chromium and copper are unusually high due to the fact that the second electron is removed from 3d5 in chromium and 3d10 in copper, which are half filled and fully filled stable configurations respectively. Okay, so here we are saying that if we talk about the second ionization energy of chromium and copper, then they are exceptionally high. Why? Because the second electron is removed from 3d5 configuration in case of chromium and from 3d10 electronic configuration for copper. Okay, if we talk about chromium, it is argon. Okay, 3d5 4s1. This is the electronic configuration of chromium, and similarly for copper you have argon 3d10 4s1. So 1 electron will be removed from this 4s orbital, right? After removal of these 1 electrons, now the second electron will be removed from this 3d5 and this 3d10, right, respectively in chromium and copper, and they are half filled and fully filled electronic configuration, very stable. That's why the second ionization energy is very high for these metals, right? Fine. Now similarly, if we compare the IE1 and IE2 for chromium and manganese, then how we can compare? First of all, if we just write the electronic configuration for chromium and manganese here. So chromium is argon 3d5 4s1. Okay, manganese is argon 3d5 4s2. These are the electronic configurations of these elements. Now first of all, I will remove 1 electron. If I'm removing 1 electron, that means I'm talking about the IE1. Okay, similarly from manganese also removing 1 electron, that is IE1. Okay, after removing this 1 electron for chromium, I will get argon 3d5 configuration. Okay, and here I will get argon 3d5 4s1 configuration. Okay, now you can see for chromium, now you have half filled configuration, whereas for the manganese you have 1 electron in the 4s. So the second electron removal is easy in case of manganese. When you will remove the second electron, it will be removed from the 4s. Now you will get the half filled configuration for the manganese, whereas the second electron will be removed from this 3d5 half filled configuration for chromium. So that's why this removal will be difficult, right? And then you will get less stable electronic configuration, that is 3d4 for the chromium. So if we compare, first of all, if we compare the IE1, then we can say that okay, IE1 for chromium will be less as compared to manganese. Why? Because in manganese initially you had 4s2 fully filled as subshell. So removing the first electron from this 4s2 configuration is difficult as compared to 4s1. So I can say that here, I can say that IE1 is greater than IE1 of IE1 for manganese. IE1 for manganese is greater than IE1 for chromium, right? Fine. But if we compare the IE2 values, then we can say IE2 of chromium will be more because you are removing the second electron from the half filled electronic configuration. So I can write IE2 of chromium is greater as compared to IE2 of manganese, right? This will be your order for the first and second ionization energy for these elements, right? Now let's see the next point. Trends in standard reduction potential SRP values. This is also a very important topic regarding the D block metals, okay? Comparing their standard reduction potential values, SRP values, okay? So stability of a particular oxidation state in solutions depend on various factors, right? like whenever you have to compare the stability of a particular oxidation state for a particular element in their solution, then we have to check their SRP values, right? Okay, and one more thing, this stability of oxidation state depends on so many factors. How? For example, if we talk about this element A, suppose we have this hypothetical element A which is converting to A2 plus aqueous. Okay, so let's talk about this element. Okay, now A solid is converting to A2 plus aqueous. This is not a single step process. Actually, this process involves so many steps. How? Let's see. First of all, this A solid will be converted to A liquid. Okay, and to convert that, what energy will be needed? That will be your delta H. Okay, you are fusing it, you are melting it, that means delta H fusion. Delta H fusion will be used here, right? Then this liquid will be converted to gas. Let's say it is converted to A gas. That means liquid converted to gas means we are talking about delta H vaporization. Okay, after converting into gas, you will remove electrons. So you will remove one electron. That means you are talking about IE1. So this will be A plus gas. But you need to remove one more electron. So removing the second electron, that means we are talking about the IE2 value. Okay. So now you will get A2 plus gas. Now you need to add this in water to get the A2 plus aqueous. So now we are adding it into water plus H2O. Now here the energy, the enthalpy change will be called as delta H hydration. Delta H hydration. Okay. So you can see different types of energies are involved in this process. First of all, delta H fusion, delta H vaporization, first and second ionization energies, and delta H hydration, right? So that's why this conversion is depending on so many factors. And here if you will compare these values, then delta H fusion plus delta H vaporization, okay, and then we have ionization energies IE1 plus IE2, okay, then you have delta H hydration. Fine. Suppose in this first step method, the change in enthalpy is delta H, let's say reaction, delta H reaction, okay. So applying the Hess law over here, I can say that this delta H reaction will be the sum of all energies involved in the second method, right? So all these, sum of all these energies will be equal to this delta H reaction. Fine. And now if we compare that, what energies are having positive sign and which energies are having negative sign, means which steps are exothermic and which steps are endothermic, then we can say delta H fusion and delta H vaporization, these values are positive, means these two steps will be endothermic in nature. These will be endothermic in nature because you have to provide some energy to convert solid into liquid and liquid into gas, right? So endothermic. Similarly, IE1 and IE2 ionization energies are also the energies which we provide. So these two are also endothermic in nature. Endothermic. Whereas the delta H hydration of the gaseous ion in water, this releases energy. So this is the only step which is exothermic here. Which is exothermic step here. So overall, the final sign of this delta H reaction will depend on the values of these energies, okay, which are involved in this whole process. If delta H hydration will have the more value, then overall answer will be negative and your delta H reaction will become negative. And the overall process will become exothermic. And we know from the thermodynamics, we know that delta G equal to delta H minus T delta S. This is the relation. And for the spontaneity of reaction, What two conditions are required? Delta S should be greater than 0. It should be positive, means entropy should be increasing in the process. Whereas delta H value, delta H should be less than 0, means exothermic reaction, right? So here, in this first step, you can see that solid is converting to aqueous. So obviously the entropy is increasing. So it is already positive. What about delta H? It should be negative. Then this process will become spontaneous in nature. Okay, so all these factors are going to decide that which oxidation state will be stable or not stable, right? Fine. Now let's see one more important point regarding this SRP. Generally, more negative value of SRP implies greater stability of oxidation state in the aqueous medium. Okay, so if we just look at the SRP values, then more negative value of SRP implies the greater stability of that oxidation state in aqueous solution. For example, if I just look at the values of SRP for titanium, first for +3 to +2, means when you are converting the +3 oxidation state of titanium to +2, then this is the value of SRP, means it is negative. That means titanium +3 does not want to get converted to +2. That means I can say +3 oxidation state is more stable for titanium as compared to +2. Similarly, for this one also it is negative, highly negative. That means titanium +2 is more stable as compared to titanium 0. Okay, titanium +2 is more stable as compared to titanium 0. Similarly here, titanium +3 will be more stable as compared to +2. These values are implies that. Okay, similarly for vanadium also you can say the same thing. Vanadium +3 is more stable as compared to +2 because it is also having the negative value. This is also highly negative, means vanadium +2 is more stable as compared to 0, right? Now here, for manganese you can see that you have a positive SRP value. Positive SRP value means the reduction of manganese +3 to +2 is very easy, very simple. It wants to get reduced. Okay, that's why it is positive. So for manganese we can say here Mn+2 is more stable, or we can say Mn+3 is less stable as compared to Mn+2 oxidation state. Okay, so depending on these values of SRP, we can compare the stability of oxidation states. Okay, one more important thing, for copper you can see the change in oxidation state from +2 to 0. This is having highly positive value. It is a positive value. That means the reduction of copper +2 to copper 0 is easy. So we can say that copper 2 plus can get converted to copper 0 easily. So 0 oxidation state is more stable as compared to +2 oxidation state for copper, right? Similarly for the other elements also we can find out. Okay. Now, the positive SRP value of copper 2 plus to copper indicates that copper has less tendency to convert into copper 2 plus, less tendency to convert into copper 2 plus, or we can say more tendency to convert into copper 0, right? And copper metal does not liberate hydrogen gas with dilute HCl and reacts only with oxidizing acids like HNO3 or concentrated sulfuric acid. This is due to the high second ionization energy of copper. Okay, so copper basically does not liberate the hydrogen gas with dilute HCl just like the other metals do. Copper does not do that, right? And it reacts only with the very strong oxidizing acids like nitric acid, concentrated sulfuric acid. These are very strong oxidizing agents. So they can oxidize the copper, okay? And the second ionization energy of copper is very high, we know, because the second electron is removed from the 3d10 electronic configuration, right? Okay. Now the next point is extra stability of Mn2 plus is due to the half-filled stable configuration. Why Mn2 plus is more stable? Why Mn2 plus is more stable as compared to Mn3 plus? Because Mn2 plus is having 3d5 electronic configuration, okay? Whereas Mn3 plus is having 3d4 outermost electronic configuration. So obviously we know that half-filled is more stable as compared to 3d4, okay? So that's why Mn2 plus is more stable. Now if we talk about chromium, chromium plus 2 is good reducing agent as it converts into more stable +3 ion. So for chromium +3 oxidation state is more stable as compared to +2, okay? That's why it is copper 2 plus is chromium 2 plus is a good reducing agent. It gets converted to chromium 3 plus easily. Okay. Now, why this chromium 3 plus is stable? Because 3 electrons remain in T2G orbitals in aqua complex like chromium H2O 3 plus. So, we know chromium plus 3 will be making this aqua complex, right, in water. And here, whenever you have 6 ligands around this metal, this will be octahedral complex. So, in octahedral field, the d orbitals get splitted into T2G and EG. Okay. So, T2G is this lower one, triply degenerate 3 orbitals, right? So, in T2G you have 3 electrons. When we talk about this D3 configuration in chromium 3 plus, it is having 3 electrons symmetrically filled in T2G. EG remains vacant, right? And due to this symmetrical arrangement of these 3 electrons in T2G, that's why this chromium plus 3 is more stable as compared to plus 2 oxidation state. Okay. Now, let's move forward. Let's see a few very important notes. VF5 is stable at room temperature, but other pentahalides of vanadium undergo hydrolysis to give oxohalides. Okay, oxohalides are VOX3. So, VF5, only this VF5, vanadium pentafluoride is stable at room temperature, but other pentahalides, they undergo hydrolysis, okay, and give oxohalides. For example, these are the cations of those oxohalides, like here VO3 plus. So, oxidation state of vanadium is plus 5, VO2 positive here also plus 5, VO2 plus, plus 4 oxidation state of vanadium. And for titanium, you have TiO2 plus, means titanium having plus 4 oxidation state, okay. And these all are called as oxocations. They are called as oxocations, right? Okay, now next point, fluorides are not stable in lower oxidation states of a metal generally, okay. Whenever fluorine is making compound with the metal, these fluorides are not stable in the lower oxidation state. For example, CuF does not exist. In the lower oxidation state of copper, that is plus 1, the fluoride will not exist, okay. Whenever fluorine is reacting with copper, because fluorine is having this very strong oxidizing nature. Fluorine is having very strong oxidizing nature. Strong oxidizing nature. That's why whenever it reacts with copper, it oxidizes the copper 0 to copper plus 2 directly. Okay. That's why CuF2 will exist, but CuF will not exist. Okay. Now, let's move forward. If we talk about CuI2 and FeI3, they also do not exist, as iodide is a very good reducing agent. If we talk about this iodide ion, it is a very strong reducing agent. So, if you have copper 2 plus, then iodide is going to reduce the copper 2 plus to copper plus 1, and CuI will be obtained as a white precipitate and iodine will be liberated. Okay. Similarly, with Fe3 plus also, iodide is acting as a strong reducing agent, reducing the Fe3 plus to Fe2 plus aqueous and self getting converted to iodine or I3 negative. Okay, fine. Next point is very important. Many copper plus compounds in aqueous solution undergo disproportionation reaction. When you have copper in plus 1 oxidation state in aqueous solution, this copper plus 1 undergoes disproportionation reaction in the aqueous solution, means it will get reduced as well as oxidized simultaneously. So, getting reduced means converting from plus 1 to 0 oxidation state and simultaneously plus 2 oxidation states. So, reduction of copper, oxidation of copper taking place simultaneously, that is called as disproportionation reaction. Okay. Now, the next is copper 2 plus aqueous is more stable than copper plus 1 aqueous due to very much negative hydration enthalpy of copper 2 plus aqueous than that of copper plus. Okay. Why this is disproportionating? Okay. Why copper plus 1 aqueous ion, this is not stable as compared to, or less stable as compared to copper 2 plus aqueous. Why? Because copper 2 plus aqueous, this copper 2 plus ion, this is having very high hydration energy. Okay, very much negative hydration enthalpy means, negative means this energy is released. So a huge amount of energy will be released by the hydration of copper 2 plus. That's why in water, plus 2 oxidation state of copper is more stable as compared to plus 1 oxidation state. Okay. Fine. Here now the next point is oxygen and fluorine stabilize maximum oxidation states of the metal. Whenever oxygen and fluorine, these two are highly electronegative elements. Fluorine most electronegative element, oxygen second most electronegative element. So when these two elements are combining with metals, metals will be present in their high or highest oxidation states. Okay. For example, MnO4 minus plus 7. Okay, MnO4 3 minus chromium, chromium having plus 6 oxidation state. Similarly, osmium tetroxide FeO4 2 minus, it is having plus 6 oxidation state. Iron having plus 6 oxidation state, that is very rare. Okay, similarly other compounds also, CrF6, VF5, etc. Okay, these all metals are having their high oxidation states with oxygen and fluorine. But very important point again, that MnF7 does not exist. Okay, manganese with 7 fluorines does not make this compound. This compound does not exist. So this is a very important point regarding these compounds. Okay, now magnetic properties. If we talk about the magnetic properties of D block elements, so what are magnetic properties? First of all, paramagnetic and diamagnetic substance. Paramagnetic substances are weakly attracted in magnetic field. On the other hand, diamagnetic substances are weakly repelled in magnetic field, right? And paramagnetic substance, they have one or more number of unpaired electrons, whereas diamagnetic substances have no unpaired electrons. Okay, so paramagnetic, to identify the paramagnetic substance, we have to look for the unpaired electrons. If there is even one unpaired electron, it will be considered as paramagnetic. When you have no unpaired electron, then it will be considered as diamagnetic substance. Okay, these show non-zero spin magnetic moment and these will show zero spin magnetic moment. What is a spin magnetic moment? Okay, this is the formula for the spin magnetic moment, mu spin only, root n plus 2 Bohr magneton, where n is the number of unpaired electron, right? So for diamagnetic substances, when number of unpaired electron are 0, so that's why the spin only magnetic moment will also become 0. Okay, fine. And we have third category also for the magnetic substance, the substance which are very strongly attracted in the applied magnetic field are said to be ferromagnetic. For example, iron, cobalt, nickel. These are the elements which are strongly attracted in the external magnetic field. That's why they are called as ferromagnetic, right? So this is the magnetic properties. Using this formula spin magnetic moment, you can calculate this magnetic moment of any ion or metal, right, of the D block. Fine. Now, formation of colored ions. D block elements, D blocks metals also have this very important property that they show colors. These ions show characteristic colors. So let's talk about the color of D block metals. Color of D block metals is explained mainly on the basis of DD transition. Now, what is this DD transition? DD transition means, you know, when these metals, they combine with certain types of ligands, certain types of compounds, their d orbitals get splitted. For example, if I talk about octahedral field, so in octahedral field, what will happen? The d orbitals will get splitted into two sets. The set of 3 d orbitals and set of 2 d orbitals, this is called as T2G and this is called as EG, right? So now this T2G and EG, they are having difference in energy. So suppose I have one electron in this T2G. So this electron will absorb some energy. It will absorb some energy and will be excited to the EG orbital, right? So first it is getting excited and going into the EG, and then it will return and will release some radiation, release some energy, right? And due to this electronic transition taking place between D and D, both are D orbitals, so taking place between these or D orbitals, this transition of electron is called as DD transition. And due to this DD transition, suppose if this emitted radiation comes in the visible region, then this particular ion or compound will look colored, okay? It will show a particular color. For example, here if we discuss, first of all the D0 ions are colorless because there is no DD transition. But even if you have one D electron, that is D1 in titanium plus 3, it shows this purple color, okay? This is due to DD transition. Similarly for other ions also, vanadium with D1 configuration is blue colored, with D2 it is green colored, and with D3 it shows violet color, okay? So in each and every oxidation state they are showing a specific characteristic color. Similarly for other metals also we can say the same thing. Chromium D3 configuration, chromium plus 3, it shows violet or green color, and chromium plus 2 shows blue color. Similarly for manganese, manganese 2 plus pink color, manganese plus 3 violet color. Iron plus 2 shows green color, iron plus 3 shows yellow color, and cobalt plus 2 shows pink color, and cobalt plus 3 shows blue color, okay? These are some colors, characteristic colors of some transition metals. Fine. Now, some very important applications of D and F block elements, okay? This is also very important, like what are the applications of these metals? So let's see. We know iron and steel, they belong to D block elements. Steel is made up of iron, it is an alloy of iron with carbon, right? So they are very important, we know. Their application is very wide. Titanium oxide, TiO, is used in pigment industry, whereas MnO2, manganese dioxide, is used in dry battery cells, okay? Zinc, nickel, cadmium, these three metals are used in batteries. Now UK copper coins are made up of copper coated steel. On the other hand, silver UK coins are made up of copper or nickel alloy, okay? Copper and nickel alloy. And if we talk about these metals used as catalyst, that is also very important application of D block metals and their compounds, that they are used as catalysts in industries. How? Vanadium pentoxide is used in contact process to form the sulfuric acid, right? We know contact process is the industrial method to prepare the sulfuric acid. On the other hand, we have Ziegler-Natta catalyst, that is the combination of titanium chloride and alkyl aluminium. Like here you have methyl aluminium, that is used to prepare the polyethenes, okay? Iron is used in Haber's process to produce ammonia. Haber's process is the industrial method to produce ammonia gas. Nickel is used for the hydrogenation. Silver bromide is used in photography, and palladium chloride is used in Baker's process, which is used to convert ethyne to ethanol, okay? So these are very important applications of D and F block elements, right? Now particularly if we talk about the F block elements, then we have to discuss few important points like oxidation states of lanthanoids and actinoids, okay? So most common oxidation state of lanthanoid is +3, and actually this point is same for the actinoid also. Actinoids also have the +3 common oxidation state, although they show other oxidation state also, like +2 and +4 oxidation states are also shown by some elements. Like here, if we talk about cerium +4, this is a very powerful oxidizing agent, okay? And +4 to +3 conversion, the SRP value is positive, that is 1.74, means cerium +4 can be converted to +3 easily because it is having positive SRP value, okay? And cerium +4 is so powerful that it can even oxidize water, but the oxidation state of water is kinetically slow. So this is cerium +4 is a very strong oxidizing agent, and generally cerium sulfate is commonly used as an oxidizing agent in aqueous medium, right? Now if we talk about europium +2 has 4f7 configuration. Still it is a powerful reducing agent and converts to europium plus 3. So even after having this half filled electronic configuration, 4f7 is half filled electronic configuration, half filled electronic configuration. Even after having this stable configuration, europium plus 2 easily converts to europium plus 3. It is a powerful reducing agent. So that's why this is a very important point. Similarly, ytterbium plus 2 is a reducing agent because it will also get converted to plus 3 oxidation state. On the other hand, terbium plus 4 is an oxidizing agent. That means it will convert into terbium plus 3 easily, okay, acting as an oxidizing agent, okay, fine. Now let's talk about the oxidation states of actinoids. So they show a wide variety of oxidation states due to comparable energies of 5F, 6D and 7S levels, okay. Here the actinoids will be showing a wide variety of oxidation state because the energies of 5F, 6D and 7S, these energies are comparable, fine. Actinoids too in general show plus 3 oxidation state, right? However, they show plus 4, plus 5, plus 6 and plus 7 oxidation states also, right? Now highest oxidation state in the actinoids is plus 7, which is exhibited by neptunium 93, plutonium 94. But it is unstable. These elements are showing this plus 7 oxidation state, but this is unstable, okay. And highest stable oxidation state is plus 6, which is shown by uranium 92, okay. Now the next point, color of lanthanoids. If we talk about the color of lanthanoids, the lanthanide ions have unpaired electrons in their 4f orbital. Thus these ions absorb visible region of light and undergo FF transition and hence exhibit color, okay. Just like the D block elements, they show color due to DD transition of elements. Here the F block elements also show color due to FF transition, means electron transition from one F orbital to another F orbital, okay. The color exhibited depends on the number of unpaired electrons in the 4f orbital, okay. More the number of unpaired electrons, more will be the intensity of color. That's what we can say, okay. The ions often with 4Fn configuration have similar color to those having 4F14 minus N configuration. If you compare the colors of the ions, so suppose you have 4F, let's say you have 4F2 configuration, then the color of this ion will be similar to that of 4F14 minus 2, that is 4F12, okay. So color of 4F2 and 4F12, these two colors, the colors of these two elements will be, or elements or ions will be similar, okay. Lanthanide ions having 4F0 and 4F14 are colorless, right? Because in 4F0 no electron in F, so no FF transition possible. In 4F14 completely filled, so here also FF transition is not possible. That's why they are colorless. The same thing applies for the actinoids as well. Actinide ions are generally colored, okay. The color of actinide ions depends upon the number of 5F electron. Here also the color will be due to the FF transition, okay. The ions containing no unpaired 4F electrons, either exactly fulfilled subshell, are colorless as expected. So here also the 5F0 and 5F14 ions will be colorless, right? Now, if we talk about the major differences between the lanthanides and actinides, so these are the major differences between these two categories of F block elements. So let's see. Lanthanides, besides the most common oxidation state plus 3, the other oxidation states are plus 2 and plus 4, okay. Whereas in actinoids, besides the most common oxidation state plus 3, the other oxidation state are plus 4, plus 5 and plus 6, okay. This is one difference. Second, lanthanides have less tendency towards complex formation, okay. If we talk about their tendency to form complexes, then lanthanides are having less tendency, whereas actinides have a stronger tendency towards complex formation. This is also very important, right? For D block elements, we say that they have very strong tendency to form complexes, and most of the complexes are formed by D block elements. But if we compare the F block elements, then as compared to lanthanides, actinides are having more tendency to form complexes, right? Next is, except for promethium, they are non-radioactive in nature. Except for promethium, all other are non-radioactive, whereas all the actinides are radioactive in nature. And the last difference is, oxides and hydroxides of lanthanides are less basic, whereas oxides and hydroxides of actinides are more basic in nature. Okay, so now we have discussed the very important properties of D block elements as well as F block elements, right? So that's it from my side on this topic. We'll be continuing this series, so stay tuned with us and do share your queries and suggestions in the comment box below, and do reach out to us whenever you have any doubt, right? And stay tuned with us for more updates. Thank you.